So we're finally getting back into some math of this, and there's two things that you guys need to understand. Of number one, what molarity is. Number two, how to prepare a solution. We've already talked about how to prepare a solution. And I told you yesterday, hint, hint, wink, wink, make sure you know how to write. And I don't mean just, I need you to be able to write it in a sentence or a paragraph form. It's more or less about 3 to 4 sentences and you're done. It's not really a whole paragraph, but it's not one sentence, of how to actually physically use tools and compounds to make a solution. And this is the math aspect of it, okay? So calculate the molarity of a solution prepared by dissolving 11.5 grams of solid NaOH in enough water to make 1.5 liters of solution. Now, we know, and again, I've started asking this in honors because I think it's important, because the problem that I've recognized is you guys don't have a clue what the question is. When you read this stuff, there's a lot of stuff going on, and you don't even know what the question in the question is. Like, what's the result? What's the purpose of me asking you this question? What are you looking for? Molarity. Circle that word right there. That's our goal. I don't care what the rest of this garbage says. I need you to find the molarity. And before you can find the molarity, do you have to know what molarity means? Yes, molarity is equal to what? Moles over liters. Now, the great news about this is, let's go to our data. Is one of the pieces of data given to us in the appropriate form? Yes, the volume is, okay? So 1.50 liters. Now, this is where AP just frustrates you, because it's the other unit in the right form. Now, we got to do a little bit to it. We've got to convert grams to what? Moles, okay? So 15, where did I get 15? Wow. 11.5 grams of NaOH. We got to go grams to moles, and I'm asking for a super nerd. Does anybody know the molar mass of sodium hydroxide? Very good, Dustin. Well done. It's 40 even. Okay. There's several that you'll begin to memorize. This is one of them. Okay. Anybody got that number? 1 mole. Oh, what's the answer? Anybody got the number of moles? Say it again. 0.28. Whoa, that's too many numbers. I need 3. So 0.288 moles. Okay. We're getting back into it. Hold your horses. Okay. So then, what do we do with this? Divide and, which is? Help. That's a great question. That's what I was fixing to ask you. My first question is, there's actually 3 ways you can write this answer. Now, I'm going to come off the screen because I want to write them in black, or actually in different colors that actually show up. There's 3 ways you can write it. 0.1, what was it? 92. You can use the units as they are. Is that appropriate? Sure. Okay. Or you can say 0.192 molar, which is the one I prefer. This is the one I would probably use. Or, in a strange way, you can do 0.1. All 3 of those are valid, acceptable answers. Yes, ma'am. Yes. Yes, that's the department of the redundancy department. Yes, ma'am. That's stupid redundant. Now, I'm going to even, actually, there's a 4th way. Now, here's the deal. I'm going to be honest with you. This is the version that I would write. This is the version you're going to see it typed in on a test. Just go ahead and forewarning you, never write it like that. That's ridiculous. Okay? But the reason, again, they type it that way is because it's easier to type an exponent than it is to type a fraction. Now, I agree with you. Wouldn't it be a whole lot easier if they just did molarity as a capital M? I agree. It would be. It would make more sense. But, again, technically mole mole per liter is more accurate than the letter M, even though it represents the same thing. I understand, but it's telling you what it is. Now, there is one thing that I would want to add to all of these at the very end to make it even more accurate. What would we want to add to all 4 of these versions? Very good. NaOH. So the 3 things we must always have: correct significant figures, the unit, and the formula if possible. So no matter what, the NaOH has to be on all 4 of them. It is a base. Very good. Okay, so hypothetically, where would your pH range? Above 7. I'm gonna go ahead and throw this at you. Since it's since it is a strong base, it's probably going to be above 12. Most strong bases are 12 to 14. Most strong acids are 0 to 2. Most, not all, but most. They're actually, in terms of how do they affect you? They're actually more dangerous than acids. Base burns are more, they eat your tissue in a different way. Acids burn through you. Bases burn from within you. Yeah, it eats your tissue a little bit different, and it's really gross. Yeah, just avoid them at all costs. Yes, ma'am. No, strong means 100% dissociation. Yes, sir. Yeah. Yeah. Exactly. That's one of the reasons why they're 100% dissociation. Okay. All right. Now, so number 2, calculate the molarity of a solution prepared by dissolving 1.56 grams of gaseous. Now that sounds odd. Gaseous hydrogen chloride in enough water to make 2.68 milliliter solution. So let me kind of give you an idea of what this setup would be. And again, don't draw this, just kind of watch. What we would have is we would have a solution of H2O. Okay? And what we're going to do is somehow, some way, we're going to have a flask. And in this flask is just going to be corked. And there's going to be a tube that comes out and runs over into this. And in this tube, we're going to have gas bubbles. Now, can you see these gas bubbles in the tube? No. And this is going to be HCl gas. Now, as soon as it comes out of the tube, what are you going to see? You're actually going to be able to physically see the bubbles. Okay? No, because here's what's going to happen. The water is actually going to dissolve. The water is going to take HCl gas plus H2O, and it's actually going to turn it into hydrogen ions plus chloride ions. Yes, before it reaches the top. Okay, it's not going to escape. It won't escape. It'll actually stay as the hydrogen chloride. Now, if it makes you feel better, if you wanted to take some sort of thing and trap it in, yes, that obviously it would help a little bit just in case one did escape, but that would be able to create your concentration. But this is possible, and the way we know that this is possible is because is oxygen dissolved into water. Yeah, that's how fish still live. Okay, so this is what's happening is that the hydrogen chloride gas is bubbled into water, and you're creating that stuff right there. Now, what is that stuff over there? Hydrochloric acid. Does that make sense? Okay. Now, you calculate the concentration of that solution based on the data. Yes, sir. What happens with the oxygen? That's a great question. Really, and I didn't want to do this, but it is what it is. Since you asked it, I'll do it. That's a great question, though. But that's really what happens. It creates hydronium, which is why whenever we calculate the pH, you're technically calculating the hydronium ion concentration. Technically, yes. I just shorthanded it because if I had written that, it would not have been very visual to you that it was hydrochloric acid. Cl minus. Okay. Calculate the molarity of a solution prepared by dissolving a 1.56 grams of gaseous hydrogen chloride in enough water to make 2.68 milliliters of solution. Again, what's the question in the question? Okay, we are looking for this stuff right here, just like we did last time. Molarity is equal to mole per liter. Now, this is the one that's going to make you even more frustrated. Is the data given to us in the appropriate units, either one of them? No. Now, what's the easiest one to change? Milliliters, converting it to volume. What do you do with the decimal which way? 3 to the left, right? So 0.0268 liters. And then the other one is 1.56 grams times 36.46 grams in 1 mole. Okay, which gives you a number of moles of what? 0.42. There's an extra 0 in there. Okay. Now, let's talk about that. He said 0.4. What'd you say? 0.42 what? 9. Let's be honest. Is it really going to make that big of a difference? You're 10,000th off. It's really going to be okay. All right, so your answer needs 3 significant figures. What'd you guys come up with? 1 point what? Now, I did add something a little different to that one this time. I did it as 1.60. If it's 6.1, that's fine. It's no big deal. But notice what I added behind the HCl. I made it aqueous because what did it tell you the state of matter of the HCl was prior to the... It said it was a gas. So you don't have to, because molar is normally understood as a solution, but it may help just clarify things a little bit better. Okay? All right, so we're good there. That's what we got. So, new skill. Sure, sounds good. Okay. Now, be careful because it may be a gaseous solution. It may be an alloy, but just make sure you put whatever the correct state of matter is behind it. Will you ever have an L that's a solution? A solution? No. But can it have a concentration? Yes. Okay, just keep that in mind. Now, new skill. We've already done this. You just haven't realized we've done it yet. Remember that thing called the ion to molecule ratio? This is what this is. Okay, so don't freak out on me. It's going to be looking at it from a little bit different perspective. So, it says we need to know the concentration of the ions in a certain compound. So I'm going to go all the way down to the bottom where it says the organ bank example. Are you one human body? Okay, so are you kind of like one compound? So the way that this is kind of like the organ bank, if your body somehow awfully perishes and we need to take some of your organs, which I encourage you to all be organ donors. It's a good thing. It doesn't matter. Personal preferences. It is what it is. I encourage you to. So here's the deal. If we take your body to the organ bank, again, you're a body. You're one body. How many eyes could we get out? How many hearts could we get? Lungs. What? Okay, 2 lungs. What about stomach? 1. Brain. Digits. It's a trick question. How many fingers? 10 fingers. Okay. Actually, yeah, really 8 and 2 thumbs. But so here's my point. What I'm trying to get you to understand is, does your body have a certain number of things within it? Do compounds have a certain number of things within it? Yes. Exact same concept. It's just a little bit different way of looking at it. You're a human. These are compounds. And compounds are made of certain numbers of things. So here's how you determine the concentration of the ions in the compound. Ions in the compound. How many different types of ions are in one compound? What are they? Very simple. Cation and anion. There is a positive thing and a negative thing. Is it possible to have more than one positive ion in a compound? Sure. Is it possible to have more than one negative ion in a compound? Absolutely. It's as simple as that. Your job is to figure out how many cations and how many anions there are in the compound to determine the concentration. Does that make sense? And here's what you do. You multiply the concentration of the solution. Prime example. If I have a 1 molar concentration of sodium hydroxide, is that the compound? That's the solution, right? So let me ask you, Sodium hydroxide. How many cations are in sodium hydroxide? 1. And what is it? Sodium. How many anions are in sodium hydroxide? What is it? Hydroxide. So here's the deal. You multiply the concentration of the solution. What I said the concentration was? 1. By the subscript of the ion. And that's the concentration of the ion in the compound. So the concentration of sodium, you told me how many sodium ions are there? 1, so it's 1 molar. You told me how many hydroxide ions are there? 1, so it's 1 molar. Okay, so what if we have strontium fluoride? All right, strontium fluoride. How many cations are there? 1. How many anions are there? 2. Strontium's a 2 plus, right? So you crisscross SrF2. So here's my question. What if the strontium fluoride concentration, originally the entire thing is 2 molar? What's the concentration of the strontium ion? 2, because it's a 1-to-1 relationship, right? What is the concentration of the fluoride ion? 4. Now, we're doing this in our brain. Let's actually look at it. So, in our first one, by the way, what is the name of that? Be very careful. What's the name of the first one? Cobalt 2 nitrate. Why do we have to throw the 2 in there? It's a transition metal and we have the reverse crisscross, all right? So since we have this, is cobalt 2 nitrate a single compound? Okay, what is the cation in this thing? Okay, so here's our cat. What is the anion in this thing? Nitrate. So here's our anion. Now, the entire solution is half a molar, right? Okay, how many cations do we have? We've got 1 of them. Okay, how many anions do we have? And go back and reread that previous bullet. You multiply the concentration of the solution by the subscript, true or false? So we are going to multiply both of these by the concentration. So what is the concentration of the cobalt ion? 0.5 molar. What's the concentration of the nitrate ion? 1. Does that make sense? Elizabeth, you good? Nicole, it doesn't. Because is that the... Alright, so let's go back and let's look at the previous slide. The previous slide says to determine the concentration of the ion in the solution, multiply the concentration of the solution. The concentration of the solution was 0.5 by the subscript of the ions. The subscript of cobalt is 1. The subscript of nitrate is 2. Does that make sense now? Question? It's given 0.5. You may have to calculate it. Okay. All right. See if you can do B. See if you can do B. All right. Read the first 3 words at the top. What is concentration's unit? What's another word for concentration? Starts with an M. Molarity. Yes. I didn't hear that. You asked me what I heard. What is the unit? I was trying to get you to talk it out yourself. Okay? Now, really simple. How many cations do we have? 1, and it's 3 plus. God bless. By the way, real quick, who can I pick on? Chance, what's the name of this thing? Very good. Iron 3 perchlorate. We all good with that? Okay. So we've got one cation. How many anions do we have? Got 3. We multiply it by the original concentration, which is 1. Can y'all see that color? 1, 1. So it's 1 molar, and this one is 3 molar. Does that make sense? We good with this? It's a very simple concept, right? Don't overcomplicate it. This is nitrate, right? There are 2 of those. Yep. Exactly. We're looking at the ion as a whole, not the elements. Sir? We're getting there. We're getting there. We're getting there. Okay? So here's your first test. Calculate the number of moles. This is a tough one. Of chloride ions in a 1.57 liter. Whatever I said. By the way, there is and I hate this. This frustrates me. By the way, it says 1.0 times 10 to the negative. The 3, you can scratch that 3 out and add it up there at the top. My apologies on that. So 1.0 times 10 to the negative 3. The 3 just went down instead of staying up there with it. Zinc chloride. Now, there's a problem. What's the question? What are we looking for? Moles of what? Moles of the chloride ion. What? Now, there is a hint at the top. The hint is moles is equal to concentration times the volume of the solution. But here's the problem. The concentration they give you is for what specifically? The zinc chloride. So, we need the moles of the chloride ion, right? So, what you do to one side, you have to do to the... So, technically, I need the concentration of the chloride ion, true? Okay? And I'm going to multiply it times what? The volume. I need the molarity, the concentration of the chloride ion. Is it possible to find? Very easy. Yes. Now, let's start with the easy part. I know there's going to be a number there. Let's start with the volume. That one's easy. What's the volume? 1.75 liters. That's the easy part. How do I find the concentration of the chloride ion? Very good. What is the concentration of the entire solution? 1.0 times 10 to the negative 3. All right? Just like we did a second ago. How many chloride ions are in zinc chloride? 2. So what do you do to that concentration? Multiply it by 2. Now, this is where it gets really weird. Is it 2.0 times 10 to the negative third? No. What is it? And I guarantee you, if I let some of you do it, you would have written 2.0 times 10 to the negative 3 down. Wait a minute. You know what? I'm being really dumb. I'm being really dumb. Completely ignore me. It is that. Here's what I was thinking, and when I say this, you'll understand. I was thinking we were squaring that number, not doubling it. My apologies. Excuse me, not doubling it. Excuse me. Shut up, you dummy. Holy crap. See, my brain is not... We're multiplying by 2, not doubling it. If you multiplied by 2... Excuse me. Holy crap. If you multiply it... If you double that number, what is it? It's 1 times 10 to the negative 6th. If you double it... The number times itself. 1 times 1 is 1. Negative 3 plus negative 3 is negative 6. I was thinking we were doubling it, not multiplying it times 2. Does that now make sense? I'm an idiot. I apologize for being an idiot. Okay? Yeah. Well, no. No. Just do. You guys are smarter than me. Do what you know to do. Just multiply it times 2. We multiplied this number by 2, which is that number. Well, no, you still have to keep the negative third. It's 2 times 1.0 times 10 to the negative 3. I just didn't, there's not another exponent, sir. Yes, which is 0.002. Bingo. That's exactly right. The reason we multiplied by 2 is because there are 2 of those. Tristan. No, that's the entire solution. Because think about this. If I have a beaker, does that beaker have a specific volume in it? Are all of those chloride ions in that same beaker? So that's the reason that's the volume. Okay? Now, what's your answer here? .5 times 10 to the negative what? Third. Now, here's the important part. You can give me a number, and congratulations, I'll give you a high five, but I'm not going to give you credit for it. Moles of what? Chloride ion. If you wrote Cl, is that accurate? No. Read the question. We need moles of what? Chloride ion, Cl minus. So this is moles of Cl minus. That minus is very important. Yes, ma'am. You're not going to get credit. Remember, there's always 3 things. The correct sig figs, the unit, and the compound. Oh, my apologies. You wrote 0.0035. I was thinking you were asking, do you have to write the negative on the CL? My apologies. You are correct. Yes. Same answer, sir. Okay? Awesome. Good job. Okay. That's exactly what we did. All right, what did you do? Yeah, it'll work. Yeah, yes, yeah. Okay. All right, go ahead and explain it then. Let's talk about it. Let's talk it out loud. You took the numbers as they are, multiplied them together. And then what'd you do? So you doubled it. You doubled in the end, we doubled in the beginning. Same thing. So you found the number of moles of the entire compound and then went to an atom to molecule ratio. Same difference. Yes. Same exact thing. You doubled in the end, we doubled in the beginning. As long as you double it, sure, absolutely it'll work for every single one. You want me to show you what he did? Okay, let me show you what he did. So he did moles of ZnCl2 is equal to the molarity times the volume, which is 1.0 times 10 to the negative third molar times 1.75. Now stay with me here. Whatever that is, he got a number right here. Pay no attention to me. Then he said that this is moles of ZnCl2, and then he did in 1 mole of ZnCl2, there are 2 moles of the chloride ion. And that was his answer. Whatever he wrote down right here was his answer. Same answer. You see, we doubled in the beginning, he doubled in the end. Same concepts. See, I prefer getting rid of stoichiometry if possible. I like visual math versus calculating math. Okay? All right, so let's look at this one. A solution is prepared by dissolving. Now, guys, this is a brand new technique and topic, so stay with me. A solution is prepared by dissolving 9.82 grams of copper chloride in enough water to make 600 milliliters of solution. That solution is then mixed with a piece of aluminum and a reaction occurs. What is the morality of the chloride ions after the reaction? That's a joke. It's a typo. It's supposed to be the molality. Now how that's yes, that thing. There is a molality. There is something called molality. Don't worry about it. You don't have to know it. It's kilograms per liter versus moles per liter. You do the mass, not moles. What? Sure, yep. Alright, so here's the deal. This is what we got to do. We need a balanced equation. I want you to do a balanced chemical equation for copper 2 chloride reacting with an aluminum solid. This is a skill you have to be proficient at. Looking at a chemical statement and getting a balanced chemical equation out of it. Copper 2 chloride and aluminum solid. This is proficiency. You have to have it. Let me say this out loud. There's a question in the statement. What type of reaction is this? Single replacement. I need you guys to know this. No matter what happens in AP chemistry, if they ever give you a single replacement reaction, always assume that it works. They're never going to give you a single replacement that does not react, unless they tell you. But always assume that they work, okay? So this one will go through. So here's what you should have gotten for your balanced chemical equation. Or actually your reaction first. Let's start there, then we'll balance it. So you should have CuCl2 plus aluminum. Now, it says it's grams, right? Actually, no. Is in enough water, so we're going to write this as aqueous. Okay, and this is plus a solid. And if you don't have all that, that's fine. So, who is aluminum going to kick out? Copper. Why copper? Why not chlorine? Okay, metals kick out metals, or cations kick out cations. Very good. So now we know that copper is going to be poor by its poor little lonesome. So I'm going to start with him first. So aluminum now is going to hook up with who? Chloride. All new compounds, when you write them, what must you check? The charges. Because is your formula going to be a little bit different than the other one? That's very important. Because if you wrote it as 2, or if you didn't write it at all, you got it wrong. You've got to check your charges when you're writing your formulas, always. Okay, now let's go in and balance it. Very good question. Yes, this would be aqueous. Go ahead. Do you know why it's Al3? ALCL. Okay. Does not matter. My first, and that's a good question. What he just asked is important for today, because as we go, it's not going to matter anymore. Does it matter what order you put them on in, as long as they're on the right side? As long as they're both products, you're good. And that's the thing, is the crazy part is you'll see as we go and we do stuff like this, everyone will write them in different orders. The key is they've got to be on the correct side of the arrow. Okay? Now, do you agree that this is our 2-3-6 rule? Okay? So we've got a 3 here and a 2 there. 3 here, 2 there. Does that make sense? Metals. Yes. Well, and I want you to think about this. If we have CuCl2 plus Al, and we try to kick out Cl2 by itself, okay? This is what I want you to pay attention. If you check your charges, this is what you would have noticed. You would have had Cu2 plus and Al 3 plus. What's wrong with that? Can 2 positives make a bond? Opposites attract likes. This is impossible. Now, this is an alloy, and this is brass, or something, but we're not talking about that. Okay. All right. So let's go back here. So here's the deal. So let's start with what we know. They tell us that we have 9.82 grams and 600 milliliters. They're wanting you to find the molarity of the chloride ions when? After the reaction. So here's the crazy part. Where is our chloride ions after the reaction? With aluminum. So we're trying to find the molarity of the chloride ions. I have one question. Is the starting information different from the resulting information? So are we going to need our balanced equation? Yes. Go ahead, Dustin. Yes, we'll get to that in just a second. Okay. So here's my first question. How do you go from one side of or from one compounded in an equation to the other compounded equation? Stoichiometry. But what's the key part that gets you from one to the other? I've got to have my mole to mole. So here's my question. I've got grams in volume. Can I get grams out of that? Excuse me, that was a stupid question. Can I get moles out of grams in volume? Yes. It's a lot of work, but it's possible. Now, I've got to get to moles. What do I do? Stoichiometry. So here's what we got to do. So I've got to do, let me change this to orange, 9.82 grams of CuCl2. Would you agree with that? Okay. Now, I know I don't need that, so I can put that on the bottom. CuCl2. Agree or disagree? Now, can I go from grams of that to moles of that? I know I can't stop there. I may not know where I'm going, but that on top I've got to get rid of, so where do at least I have to put it? Got to put it at the bottom. So moles of CuCl2. I asked you just a minute ago, what's the only way to get from one compound to the other? Am I at my mole to mole step? Yes. And I'll stop right here and I'll answer questions. Now, Dustin, does that answer your question? Does that make sense now? Okay, question. Somebody have one. Why what? Let me ask you this. Are you proving that you're doing your work? You have to prove it. It has to make a flow. It has to make sense. Now, here's the next question. Do I stop here or do I keep going? Pulse. What's the question? I'm looking for molarity. So let's stop here. So if I need the molarity of the chloride ion, what does molarity represent? Now, the easy part is the liters. Would you agree? How many volume units do I have up there? 1. And it is what? Now, milliliters. 0.600 liters. Now, the reason I stopped here to ask this question is, do I stop here? This is the most important question. What am I currently sitting at unit-wise? Moles of aluminum chloride. I need moles of what? Chloride. So I need one more step. Yes. Let's go one more step. Now, what's that? Okay. Now, I may not have a clue where I'm going, but if what's on top has to go where? It's got to go on the bottom. So I've got moles of AlCl3 on the bottom. At this point, here's what scares me. What do you naturally tend to want to go to here? You want to tend to go to grams. Why can't we do that? We got to get to the moles of chloride. Can you go from moles of aluminum chloride to moles of chloride? Yes, you can. Very good. This is our molecule to atom ratio. Does that make sense? Okay. So, this is why I said this is new. You've never seen this. We've never gone from mole to mole again. And I know that looks crazy. Now do you see why I stress to you, write the compounds in your Stoich? If you didn't have that written, you would look at that and say, what the hell is that? I threw that one at you for a reason. Now, from this part, let's start with the easy one. Let's start with our compound to compound mole to mole. Now, this is, and I know this sounds really crazy, this is our compound to compound. Where do these numbers come from? Very good. These are from the coefficients. And I know that's really hard to see. This is what we've always done, right? What's your top to bottom mole to mole? 2/3. Are we cool with that? Okay, let's look at the right one. This is, now, I know what you guys said, but I'm going to write it like this. Ion to compound ratio. Why did I say ion and not atom? Because technically, isn't it an ion? So, whoa. Where do these come from? Subscripts. So, for every 1 aluminum chloride, there are how many chlorides? There are 3. You with me on this? So stop. Let's stop here if this doesn't make sense. Let me actually ask this. Do you agree that the first step that we have blank, that's easy? This is not an issue. Every one of you can do this. I want to make sure that the yellow and the white is clear. Does anyone have a question? Now's the time to ask. Nicole? What now? When you say that, what? Look up here and what color are you referring to? Okay? This is not the coefficients. This is the subscripts. So when you see AlCl3, for every one of those things, how many chlorines are there? 3. That's why it's a 3-to-1. Does that make sense? We all cool with that? Any other questions? Now, this is where I need your help. Let's come back to the mass. What is the mass of copper 2 chloride? 134.45. Okay? All right. So now, we need an answer. And we're still quite not done yet. Because once we get our number from this math, we got to plug it into another formula. And I agree. This is long. This is arduous. This is challenging. But if you really think about it, it's not that difficult. Yeah, give me your number of moles of chloride ion. Here's the important question. If I tried to do this for you guys last year, it would have blown your skulls out. It would have. But the foundation that you now have, the one new thing that we've added one thing. One. There's only one new thing on this board that you've never seen. We went from our mole of compound to mole of compound to mole of compound to mole of ion. You've never seen this step. That's the only new thing that you've never seen. And I asked you a minute ago, that last orange step, traditionally, you were used to converting from moles to what? All we did was change it to the moles of the ion. That's the only difference. This part right here, this is it. That's the only difference in this entire question that you've never seen before. So think about it from that standpoint. All of this isn't new. Just that thing in the yellow circle. Yes, sir. Now, here's the last part, and this is the part where it gets easy. We now have to plug it in right here. But my question to you guys is, and I think it's an important question to ask, why do I even need that top part? Again, what is the question? What is the molarity? And what is molarity? Mole per liter. Now do you know why you have to actually do this last little step? It's crazy, but you have to answer the question. And that's why I'm stressing to you guys, the question is important. Because if you left it as moles of chloride ion, did you answer the question? No, you did part of it. You would have earned a point or two, but you wouldn't have earned full credit because you didn't answer the question. How easy is it to actually get full credit? You divide it by a number already given to you in the problem. Pretty simple. Okay? How do I know what number it was for? All right, that's a good question. Do you agree it says a solution is prepared by dissolving 8.9 grams of copper 2 chloride in enough water to make a 600 milliliter solution? That beaker starts at 600 milliliters. Did all of this occur in that same 600 milliliter beaker? That's how I know what the volume is. Okay? Did I really? I think I'm getting dyslexic. Now, what's your final concentration? So 0.243 molar chloride ion. That's a great question to end on, isn't it? We'll end there. Now, don't forget, today is ASE. We will be coming back. Yes, ma'am. No. Yeah, we have to do that. And we're going to make it easier this time.